Welcome learners. In today's lecture, we are going to start the second chapter of the main textbook. This is by Robert Boylston and Louis Neshelski, and we are following the 11th edition for the course of Electronic Devices and Circuit Theory. In this chapter, we are going to further look into various applications associated with our first semiconductor device, and that is diode. So now let us have a look at the objectives that we are going to cover in this chapter. So in this chapter, we are going to understand what is load line analysis associated with any electronic device. In this case, the electronic device will be a semiconductor diode. Second, we are going to see the equivalent circuits that help us analyze a diode in a series combination, a parallel combination, and then we will see the series and parallel combination. Following that, in our next lecture series, we are going to talk about what is rectification, especially the half wave rectification and full wave rectification. Following that, we'll talk about diode based circuits known as clippers and clampers, and finally we are going to look into a special kind of semiconductor diode which is known as Zener diodes. The specialty about these diodes is that they are operable in the forward bias direction as a normal PN diode, but they are also able to operate in the reverse bias region, and hence they have this kind of a specialty that even before reaching the breakdown voltage, they can give us an important amount of output current. So these are the 5 objectives that we are going to see in the lecture series from the second chapter. So let us first begin with the first topic at hand, which is about load line analysis. So before we dive into the images in front of you, let us first understand what is load line and why it is used. So normally load line is a graphical approach. So it is a graphical approach to find what? To find the Q point, or we can say to find the load line which intersects with the characteristics of the electronic device, or with the characteristic curve of any device, in this case a diode. So it is normally applied to non-linear devices, meaning those which don't follow the Ohm's law, which doesn't follow the Ohm's law. So basically we can say that load line explains the constraints other elements put, other circuit elements put or have on the diode in any given circuit, a network or a circuit. So basically load line tells us that how much the load is coming from any other element onto the diode. If we take any circuit, for example, if you look at this figure and first part of it, we can see that in this circuit, this is a voltage source represented by E. It can be a DC or an AC source. Here it is a DC source. Then we have a diode which is connected in series to the load, which is the resistor. So load line is basically going to tell us that what is the amount of load which the diode is taking coming from other elements in the circuit, that can be a voltage source or a resistor as shown in front of us. So basically in order to find the load line, the first thing we do is see the characteristics of the element. So in the part B of this image, we can see that the voltage and current ratio known as the characteristic curve is shown over here. So this is again our famous characteristic curve for the diode. And we can see now what is going to happen is that whenever any circuit element is introduced in a circuit, what is going to happen to that diode's behavior, and that behavior is basically given in the form of the load line, which is shown over here. So the idea or the objective is that where the load line is going to be drawn with reference to the characteristic curve, thus from this both lines drawn we can find an intersection point which is going to be our new Q point, and thus if we know the Q point, then we can find the resistance and all the associated things which we talked about in our previous lecture. So let us do the analysis of this load line. So let us say if we are given any circuit as shown over here, and the objective is to figure out how to draw this black colored load line onto the characteristic curve. So we already have this information, that any circuit will be given to us, and we also know the behavior of any semiconductor diode, which is represented by its characteristic curve. So we need to figure out how to draw this load line and what are going to be its initial or maximum current and maximum voltage values shown over here. So normally we begin by doing the analysis as such. We look at the circuit and we apply what is known as the KVL on this circuit. So if you don't remember, I'll upload the lecture series on the Kirchhoff's voltage and current law at the end of this lecture, and you can revisit those to refresh your memory. So just to let you know that the Kirchhoff's voltage law is basically takes the algebraic sum of all the voltages in any network, and so if we take the algebraic sum of all the voltage in any network, it should be equal to 0. So this is the mathematical expression of Kirchhoff's voltage law. And when doing the analysis of any circuit using KVL, we either move in the clockwise direction or we can go in the anti-clockwise direction. And moving in this direction, we define certain nomenclature that what is going to be the voltages signs appearing for each circuit element in the circuit. If we consider this book specifically, it has taken the analogy that whenever any circuit element has a negative sign in the start and it is moving towards a positive sign, which we normally call as voltage rise, so we are going to associate a positive value with that. Similarly, if we have a sign or any element that has a plus sign or a positive polarity at the entering of it, and the out polarity is negative sign, which we called as a voltage drop, the author has taken a negative sign to associate with that circuit element. So now let us apply this KVL on this circuit. So when applying KVL, we start and move towards the clockwise direction in the outer loop. So the first thing we encounter is the negative sign for the voltage. So whenever we have a negative sign, we are going to associate a positive sign. So we can say it is going to be plus of E. Then the next element we encounter is the diode, which is having a positive sign, so which means that we are going to take a negative sign with it and we are going to write the voltage across the diode. The next thing that we encounter is the resistor, and it has a positive sign or positive polarity as on its input, so we are going to associate a negative sign and we are going to write V of we can say V of L for the load equals to 0. So the algebraic sum of all the voltages in this circuit is not equal to 0, and this is defined by the Kirchhoff's voltage law. We can further simplify this as E is equal to Vd plus VL. We can further simplify it as Vd, and this region can be further simplified using the Ohm's law. So we can write it as Id by RL. Let us say this is our equation 1. So what we are seeing here is that we have taken the clockwise loop for the flow of current. So if this is my current Id and we have taken this loop, so the current that enters the diode is represented by Id, and the same current when it leaves the diodes and enter the resistor, it is now represented by IR. And again we can do this because we have a second principle known as the Kirchhoff's current law, which states that for any given node the amount of entering current should be equal to the amount of current that is leaving. So this is known as the KCL. So this is the first equation we have. Now what we want to do is we want to calculate the maximum values for the current and the voltage. So in order to do this, we can just from equation 1 we can do this. We can calculate the current I of D and we can calculate the voltage V of D. So in order to calculate the current, what we can do is, in the equation number 1, let us take Vd equals to 0 volts. So this means that our equation 1 in form of the current will be equal to E divided by RL. So this will be the maximum value, and you can see over here that the maximum value we got for the current is E divided by RL. Similarly, in order to calculate the voltage, in the equation number 1 we are going to take our current ID equals to 0 amps, thus our voltage Vd is going to be equal to V, and we can see that the maximum voltage we get is E over here. So this is how we calculate the maximum points of the load line. Once we know the values of current E by R and voltage E, we can just draw this black colored load line from these or within these 2 points, and thus we are going to see that where is this load line is going to intersect with this blue characteristic curve. The point where it intersects, we get the Q point. Once we know the Q point, we can do our previous analysis where we can find the IDQ and VDQ, and we can also find the resistance associated with it. If it's a DC source, the resistance will be the ratio of the Ohm's law, which is going to be VDQ and IDQ. So this is what we have already seen in our previous lecture. We already know that Q point is known as a quiescent point, which means something that is still not changing or not varying. So this is how we do the load line analysis, and we can also verify that the equations we have figured out for the maximum current and voltage are also representing a slope. How we can do that? So we can also say that the equation we have represented is acting as a slope. For example, this is the load line which we got. So let's say this is our load line. This was the maximum voltage. So this is voltage Vd, this is maximum Id, this is 0. So the value of maximum current and voltage comes out to be these points, and the slope, this is basically a falling slope over here. So we can also verify that this line, the load line that we have just drawn, is following a decreasing slope, and we can mathematically prove it. Again, from the equation 1 we got E equals to Vd plus Id into RL. This was our equation number 1. So we can mathematically see that if we divide this equation by the value of load resistance RL, then it becomes Vd by RL plus Id. Now we can find the value of Id, or we can take it to the other side, so it becomes minus Vd by RL plus E by RL. Thus, if we compare this equation to the equation of a slope, we know that equation of the slope is y equals to mx plus c. So if we compare it in regards to this, so we know that on the y-axis we have the current Id shown over here. On the x-axis we have the voltage, which is going to be Vd by RL. So this is the voltage over here. So this is basically the x-axis, and the slope is E by RL. So we can say that this is basically a falling slope because there we have a negative sign over here. So we can say that the value of the C from this equation, which is the intercept, is E by RL. Value of x is basically Vd by RL with a negative sign, and value of y is basically your Id. So hence we can confirm that this is indeed a falling slope. Another thing to note here is, especially for the value of the current, we see that the load line which we have drawn, is mostly dependent upon the value of resistance. So if the value of resistance is increased or decreased, the slope line is also going to change its behavior, and thus if its behavior is changed, the Q point is also going to be affected. So For the current state, the Q point might be over here, but if the value of resistance is increased, we might see that the slope moves from this point to something over here. So we can have the value moved to this point. Again, in this scenario, the Q point might change. If the value of the resistance is decreased, the slope might move in the upward direction. So these are the scenarios that we are going to look in the coming lectures, but just to give you a introduction or a brief intro that what is the effect of resistance, and we can see that it's a vice versa relationship. So now let us look into an example and see how we can solve these kinds of problems. So in this problem or example, we have been given a circuit and the characteristic curve of the semiconductor diode is shown over here, and we have been asked to find in part A VDQ and IDQ, and in the second part we have been asked to find the value of VR, or what is the voltage across the resistor. So in order to do our analysis, we follow certain steps, and the certain steps are that for the given circuit we first apply KVL, then we find ID and VD to get the maximum points for the load line which needs to be drawn on this characteristic curve shown in part B, and finally wherever the load line intersects with this characteristic curve, we will get the Q point, and from that Q point we can find IDQ and VDQ. So if we apply this technique, so let us start with the first step. For the given circuit, we apply the KVL. So we see that the diode is connected in series, and we take the clockwise direction for the flow of current like this. So if we apply KVL, Kirchhoff's voltage law, we will get equation to something like this. So the entering side is a negative one, so it is going to be plus E. Then we have a diode, let us say it's a silicon diode. Again, the entering side is positive, the voltage, so we are going to take negative V of D. Then for the resistor, the entering side is positive, so we are going to take negative V of R equals to 0. We can simplify this equation in terms of the Ohm's law at the load resistor, so we can write it as ID RL equals to 0. Let us say this is our equation number 1. So now what was the step? In order to, so the next step is to find the ID by making one of the voltages equals to 0. Similarly, for the third step, we can find VD by making ID equals to 0. So let us find VD. So when VD equals to 0, what is going to happen in equation number 1? The value of ID is going to be E divided by RL. We know the value of E is 10 volts and the load resistor is 0.5 kilo ohm. So the current value comes out to be 20 milliamps. So this is the current that we are having. Secondly, now what happens in equation number 1? We are going to take the current now equal to 0. Once we do this, the value of VD is going to be E, which is going to be 10 volts. So we have figured out the maximum values of the current and voltage such that the load line can be drawn. So let us see where the load line is going to appear. So for the same characteristic curve, let us enhance the curve and see where the load line is. So we have the same characteristic curve, and you can see the value of the current is 20 milliamps as we saw previously, shown over here, and for the voltage, the maximum value or the horizontal axis should be at 10 volts. So this is the 10 volt. Thus, once we have these 2 points, we have drawn the load line shown here in the black color, and the point where the load line intersects with the blue characteristic curve of the diode, this is going to be our Q point. Once we have figured out Q point, the next step is to find the unknown, which is the VDQ and IDQ. So from this Q point, if we extend our axis, we get the value of IDQ, which is at 18.5 milliamps, and if we extend it towards the voltage scale, we get the value of VDQ at 0.78 volts, and thus we have figured out the required VDQ and IDQ for this numerical example. Finally, we can also find how much is the resistance associated with this. So we use the DC resistance equation to figure out that for this scenario, the resistance of the system or the resistance taken by the diode will be around 42.16 ohm. So this is how we find the load line, the Q point, associated voltages and currents, and if you want, we can find the resistance. In the final or the second part of the problem, we were asked to find what is the voltage across this resistor. So in order to find voltage drop, we previously saw that if we apply the KVL, it's going to be just the difference of the voltage source and the voltage appearing across the silicon diode. So it is going to be VR equals to E minus VD. E is the 10 volt source, and we are going to apply the voltage which is already figured out as VDQ over here. Thus we get that the voltage appearing across the load resistor or the resistor is going to be 9.22 volts. So that is a simple problem where we find the load line and the values associated with it. So let us now look into this example with another perspective. Let us say for the same example, we have been asked to use the diode's equivalent models and figure out what is going to be its behavior when we use the approximate equivalent model. So, or you remember there were three equivalent models for diode. The first one was the piecewise linear equivalent model. The second one was called simplified, simple or approximate model, which we have been asked to utilize, and the third one was the ideal equivalent circuit model for the semiconductor diode. So now we have been asked that for the same set of problems you use the approximate model. Now what is going to happen when we use the approximate model? The circuit remains the same. So the circuit will remain the same. The only thing that is going to change is the characteristic curve of this signal. So our circuit remains the same. So let me draw it over here. We have a DC source followed by our diode, and then we have a load. Our DC source was of 10 volts. We had a silicon diode, and then we had the voltage of this resistor over here. So let us see what is going to happen. As I mentioned, when we use the approximate model, the characteristic curve is going to change. So now instead of a curve which we saw over here, which was a non-linear, for the approximate model, our curve is going to be a straight line having a 90-degree angle. And this is because the model, the approximate model, if you remember, is having the configuration as such that instead of using this physical diode, we replaced it with its approximate model, which is going to be the voltage supply and the ideal diode. So remember that this is not a battery, this is 0.7 voltage, knee voltage. So this diode is going to be replaced by this equivalent model, and this is the symbol of an ideal diode. So you can see that the value of E by RL and the E remains the same. The IDQ or the Q point also remains the same. The only thing is that VDQ has been reduced from 0.78 to just 0.7 because the model has now been changed from non-linear to an approximate model. So what is going to be the effect? The effect is that the resistance is going to get improved. So previously we had a resistance of 42 ohm, now the resistance has decreased to 37.84. Similarly, if we again go to this problem and instead of using the approximate model, we are asked to use an ideal diode model. Again, what is going to happen in the ideal diode model? The only element we have is the ideal diode. The symbol is such, which means that in the ideal diode model, this behaves as a short circuit, where the voltage of the diode is going to be 0 volts and we are going to get the maximum current. Such our characteristic curve now becomes something like this. So it is just having a maximum value at 0 volts. Rest of the elements remain same. The only thing is that the Q point is not going to change because previously it was intersecting with the blue curve after a rise of 0.7. Now the current is at 0 volts, a maximum value. So the Q point or the IDQ point is going to be at 20 milliamps and the voltage VDQ is going to be at 0 volt. Thus our resistance is now going to be nothing because the voltage in a short circuit equals to 0. So this is the change that we normally have whenever we are working with VDQs and IDQs, and we have to be very careful when changing the behavior of the system. If we are using an approximate model, the characteristic curve is going to change and our analysis or the Q point is going to be different. If we are using the ideal model, we can see that the characteristic curve has just become vertical at voltage is equal to 0 volts. So this is the load line analysis that we have. Moving on, Now let us come to the second portion, which is basically talking about the diode configuration. So the diode configuration is basically in two ways. We are going to look into three categories. The first is if the diode in any circuit is placed in the series configuration. So again, you can visit the linear circuit analysis lectures. I'll share the link over here to understand what do we mean by series combination, parallel combination, or series parallel combination. So series combination is something where the flow of current is in a single path or same path. There is no deviation of the flow of current. So as you can see over here that the current ID is just following this loop. So we can say that the diode is connected in a series form. Another thing, if we have more than one elements in a circuit, and how we can identify series combination is that the tail of one is connected to the head of other. So let us say if we have a voltage source and we have one diode connected over here, other diode connected over here, and then we have a load resistor. So if this is our voltage source, this is silicon diode 1, this is silicon diode 2. So again we can say that these diodes are connected in series because the tail of one is connected to the head of the other. So this is basically the basic definition of series configuration, but we normally associate the flow of current or the direction of current to identify if the circuit is in series or in parallel. Obviously, if you talk about the parallel, then the current will have multiple paths to flow through. So let us first focus on the series configuration. So in a series combination, we can see the basic circuit where the diode is connected in series. We have a voltage source represented by E and the resistors with the respective voltages and current. So in the questions associated in this textbook for solving the diode configurations, whether it is series parallel or series parallel combined, we are going to use two equivalent model schemes. The first is going to be the approximate model and the second is going to be the ideal model. Just to inform you again that for the approximate model, the characteristic curve behavior is such that at the forward bias voltage of 0.7 volt, we get the maximum value of the current and the angle made is 90 degree. In our circuit analysis, we are going to replace the symbol of the diode with its equivalent model to make our analysis or KVL a bit easy or understandable. If we are using the forward bias condition shown over here, our circuit's symbols and behavior will be such. If we are in the reverse bias condition over here where there is no conduction, then our diode will be replaced by an open circuit. And if we are talking about the ideal model, so again at 0 volts when VDE is equal to 0, we are going to have the maximum current, which means that our system or our symbol of diode is going to be replaced with a short circuit, and we know in short circuit from Ohm's law there is voltage which is 0 volts. And if we are in the reverse bias condition, for the ideal case, our diode symbol will be replaced with an open circuit. So again, these are the things which we have seen in our previous lectures, but just to refresh your memory, they have been introduced over here. So now let us see how we are going to solve diodes which are connected in series configuration and figure out the unknown parameters, either voltages or currents. So there are few steps associated and few equations have been provided to you to make your analysis a bit easier. Again, these equations shown over here are basically derived from the Kirchhoff's voltage law. So the idea or the steps involved in solving these configurations will be that the first thing, let me write it over here. So the steps needed to solve the series diode configuration. The first is we need to check whether the diode is in the on state or the off state. So we have to check. How can we check it? We are going to match the current flow with the diode arrowhead. If they are aligned, we say that the diode is in the on condition. What does it mean? Look over here. This is the symbol of diode. This is its arrowhead. So if the direction or the flow of current is in the same path as the arrowhead of the silicon diode, we say that the diode is in the on state. So this is what it means. So if the current is flowing as such and the diode arrow is in the same direction, we say that it is in the on state. If diode arrow has it like this and the current is moving in the opposite direction, we say it is in the off state. So this is what it means to follow the direction of the current and see the arrowhead of the, or the symbol arrowhead of the diode. The second thing, we are going to replace, so the second step, let me change the colors. So the second step is going to be that we are going to replace the diode, the symbol of diode, with its equivalent circuit. It can be approximate or ideal model. The third is, again, we can apply KVL and KCL, the main equations, or we can start with these basic set of equations that have been derived from KVL and KCL. And the final point is, we can then confirm the main thing associated, or the final point is that always confirm the voltage applied, or the provided voltage source, applied voltage is enough to forward bias the diode. What does it mean is that if we are using a silicon based diode, then we have to make sure that the power supply, the battery over here, should have a minimum voltage of 0.7 volts. If we are using germanium material, then the power source should generate a minimum voltage of 0.3 volts. So this is what it means, that we have to make sure that enough voltage is being generated so that the diode can work in the forward bias direction. So now let us use these steps to solve various examples for the series diode configuration. Later on we are going to solve the parallel diode configuration and then series parallel combined. So in this example, we have been given a circuit and we have been asked that for this series diode configuration, find value of the voltage appearing across the diode, the voltage appearing across the resistor, and the current flowing through this resistor. So what we can do is, we can directly apply these steps and we can change this to our given steps. So the step was, first we have to see whether the diode is in the on state or not. So if we look at the arrowhead and the flow of current, it is in the same direction. So we can say, so the first step is check that diode is in the on state. So this is check. The second point was to replace the symbol of diode with its equivalent circuit model. So let us say if we are talking about approximate model, the diode is going to be replaced with its equivalent circuit model, which is going to be something like this, 0.7 volts. Before applying the third step, we can go to the fourth step, that was to see whether enough voltage is available to make the diode forward bias, and we can see we have the voltage of 8 volts. So 8 volts is far greater than the forward bias condition of 0.7, so the current is going to be conducted. And finally, the third step was to apply the equations, or extract it from the KVL and KCL. So the equations are these three. So we can directly apply these equations to figure out the unknowns. So let us see how can we redraw this circuit. So this is going to be our voltage source. The diode is going to be replaced by its equivalent circuit, and then we can have our resistor over here. So this is the value of E, this is 0.7 volts, and this is 2.2 kilo ohm, and the flow of current or the KVL that we are taking is in the clockwise direction. So now we need to find voltage VD. So voltage VD, so always keep in mind that the voltage across the diode is going to be its forward bias voltage. So which means that for this case it is always going to be its knee voltage, which is 0.7 volts. Hence we can also verify that the voltage at the diode is going to be its knee voltage, which is 0.7. The second part is to find the voltage across the resistor. So this is voltage across the resistor is basically, if we take the outer loop and apply KVL, so it is going to be the difference of the main voltage source E and the voltage across the diode. So it is going to be 8 minus 0.7 volts, and this is also confirmed from this equation over here. So this comes out to be 7.3 volts. And finally, if you want to find the current ID, so the current ID is going to be the Ohm's law, which is going to be VR divided by R, and it comes out to be 3.32 milliamps. So this is the three sets of equations that we have used to find the unknowns in this series diode configuration. So you can also verify, I'll just get rid of these. So This is the same results that we got, V of D, V of R, and 3.3 volts. So this is how we solve the series diode configuration. Now what happens if we change the direction of the diode? If the diode is reverse, meaning now we place the diode as such. So the first condition is going to violate the first condition, because the current is flowing in this direction but the arrowhead is in the opposite direction. This means that the diode is going to be in the off state. Since it is in the off state, we can replace the diode with an open circuit. Now once we do that, what is going to be the value of VD, VR and ID for the second scenario when the diode is reversed? So what is going to be VD, what is going to be VR, what is going to be ID? So we know that when we have an open circuit connection, the current is unable to flow because there is a gap. So which means automatically the current will be 0 amps. What about the voltage across the resistance? Say there is no current flowing over here, so the resistance or the voltage is going to be 0 volts. Now what about the voltage appearing at this open circuit junction? So the voltage appearing here is just going to be the source voltage, which is going to be 8 volts. And thus this is how we solve the diode's problem. And you can also verify that this is what we have as well when talking about the voltage VD. So it is going to be 8 volts and the current is obviously going to be 0, which we just saw. So this is how we solve the series diode configuration, keeping in mind the steps. If you practice enough, then you won't need to know these steps because your memory will know how to solve these. Let us look at further examples of series configuration and interesting ones. So before we proceed with this example, we have been notified that a new symbol is introduced in our analysis, and that is that we are going to simplify the circuit. Simplify the circuit is such a way that the applied battery is now going to be replaced with this circular notch. So this is known as a circular notch. So what does it mean? Whenever we see this circular notch having different polarity signs, for example here the polarity is plus 10 volts, which means that our circuit is connected to the positive side of the terminal and the negative side is connected towards the battery. Similarly, if we see a circular notch with a negative voltage, which this means that our negative polarity is at a higher potential and the positive polarity is connected towards the ground. So this is what this circular notch means. Now let us put this to a test and understand with an example. So for this circuit configuration, we again need to find the voltage across the diode, voltage across the resistor and the current flowing through the diode. So here we see this notch is provided with a value of 0.5 volt. What does it mean? That if we extend this plus 5 volts, which means that this is connected to the positive or higher polarity and the negative is connected towards the ground. So this is what this notch is indicating. If it had been a negative value, then the polarity over here would have been at negative and the positive would have been towards the ground. So this is what this notch is telling us. Now once we know this notch, let us see what can we do. So again, if we follow the steps, we would like to see whether the diode is in the on condition or the off condition. So we can see that the direction of current is similar to the arrowhead, so the diode should be in the on state. The second is we can replace this diode with its equivalent circuit model. Okay, this is what we can do. So we can replace this diode with its equivalent circuit model. If you are using the approximate model, this can be replaced by its symbol. So this will be 0.7 volts, which is basically Vk. If it's an ideal model, the diode will remain the same. Thirdly, before applying KVL, we need to see that whether this diode is going to conduct or not, whether enough voltage is applied or not. And we can see that 0.5 volt is less than the required biasing condition of knee voltage, which is 0.7 volt. This means that this diode is not going to conduct, and thus if we apply the KVL and KCL rules to find these unknowns, what are we going to have? We are going to see that VD is going to be 0 volts, because since the voltage source or applied source is not enough, this diode is going to be replaced with an open circuit connection, which means that we will have something like this. So or we can have a better understanding like this. So since the voltage is not enough, our diode is now replaced with an open circuit. Since it's an open circuit, we automatically see that the current is going to be 0, the voltage across the resistor is going to be 0, but what about the voltage? So the voltage Vd across the diode is going to be the same as the source voltage, which is going to be E. So here you can see that Vd is going to be 0.7 volt, and for the ideal model the 90° is created over here, and thus our equation will have these values, and it is also confirmed from this box over here. So again, this was a very interesting question, that following the steps, although the diode was in the on state, the equivalent circuit was replaced, but the applied voltage was not sufficient to make the diode work in the forward bias, and thus we had a reverse bias condition where the diode is replaced with its open circuit value, and thus if it's an open circuit, the only thing that is going to exist is the source voltage on these terminals. The other values, the currents and the voltage across resistor, will be equal to 0. Let us look to some few examples or more examples associated with the series diode configuration. Again, in this we need to find the output voltage V0 and the current flowing through this diode ID. So if we look at this, we know that the direction of current is following the arrowhead. So the diode, both the diodes in this case, are in the on state silicon, and the next is the LED. The symbol over here represents a light emitting diode. So the second step is we replace this with its approximate model. So this is the approximate model, where we have even simplified this notch and represented it as its complete battery. The silicon diode is replaced by its approximate model having the value of 0.7, and the LED is made in the on state condition when the voltage reaches 1.8 volt, and thus we have a resistor and the output source. The third thing is to verify the voltage applied is enough so that both the diodes are in the forward bias condition, and yes, 12 volt is far greater than the forward bias condition for silicon, which is 0.7 volt, and 1.8 volt for the LED. So this condition is also met. Thus we can apply our KVL to find the unknown voltage V0 and the current I of D. So again, the V0 is easily found if we apply the KVL on the outer loop. So our equation will be, if we take the negative sign over here, it is going to be E minus, we have a positive sign, so it is going to be minus VK1. Then we have a positive sign, it is going to be minus VK2. Then we have the voltage at output, so it is going to be minus V0 equals to 0. So V0 is going to be 12 minus 0.7 minus 1.8, and it comes out to be the value will be something we'll see shortly. Similarly, once we have found, let's say, X volts, so once we have found the V out, we can easily find the resistance over here by applying the Ohm's law. So IR is going to be VR by R, where VR is V0 by R, and thus we should get something in amps over here. Let us verify this. Okay, so the output voltage comes out to be 9.5 volts and the current comes out to be 13.97 milliamps. I'll just remove these so that the image is, or the result is, clearly visible. So this is what we got in terms of the output voltage and the current flowing through the diode. Let us again look to few more interesting examples. So here these are very interesting examples, so let us try to solve them one at a time. So in the first problem, again we need to find the output voltage V0 and the current flowing. What is the first step we do? We see whether the diode is in the on condition or the off condition. So we can see that the direction of current and the arrowhead is in the same direction. So this is in the on condition. Secondly, if the voltage applied is enough or not for the silicon diode to work. Again, yes, 5 volts is far greater than the 0.7 volts, so the diode is going to work. We can replace it with its equivalent model. So this diode can be replaced with its equivalent model. Let's say if you want to replace it, it is going to be something like this. So like this. So it is going to be V of K, and this is going to be plus, and this is going to be minus 0.7 volts. So now if we do our analysis, this is going to be straightforward. If we apply KVL on this loop, so we can write it as, we can go in both directions, in counterclockwise or clockwise. It's up to you. If you are comfortable with the clockwise, you can go in this direction as well. So say minus 5 volts plus 0.7 volt is equal to V0, and thus V0 comes out to be minus 4.3 volts. So this is the KVL applied. Similarly, if you want to find the current, we can just use Ohm's law over here. So the current ID is going to be V naught by R, and it comes out to be 1.95 milliamps. So this is the solution for the current and the voltages that we are going to use. So coming to the second question, we need to find V naught. So again, it's a straightforward, again the direction of current, if we take like this is the clockwise direction. So the direction of current follows the arrowhead. So both the silicon and germanium are in the odd state. The applied voltage is 20 volts, which is sufficiently enough for the analysis. So we can just apply the KVL equation to get the equation. So I'm just going to write the equation. It is going to be 20 minus 0.7 knee voltage for silicon minus 0.3 for diode. Then if we take this path, this is going to be minus 2 ID minus 2 ID equals to 0. So the current is flowing over here and the same current is going over here. So then the analysis comes out to be, first we need to figure out the current from this equation. So the current comes out to be 4.75 milliamps. Finally, once we know the current, we can find V naught using this loop. So V naught minus 2 ID equals to 0. So V naught is basically 9.5 volts. So this is the solution to the second problem. The third one, again quite similar. We need to find the output voltage and the current. Again, the direction of current follows the arrowhead. So the silicon is in the on state. The voltage applied is enough on both the sides. So how can we solve this? So we can just apply the KVL on this loop over here. So it is going to be 20 minus 6.8, let's say ID minus 0.7 equals to minus 10 volts. So I have just taken the upper track. So here the value of ID then comes out to be 4.3 milliamps. Once we know this, we can easily find V naught, which is going to be 20 minus 6.8 into ID. We have already the value of ID, which is 4.3, so it comes out to be 9.3 volts. So these were some interesting questions associated with series combination or series diode configuration, and this is the way you can find these unknown voltages and currents. So now moving on, let us talk about diodes connected in parallel. So the parallel connection comes when the direction or the path of current has multiple ways to go. So you can see if we have this current I1, it can go in this direction and also can follow this direction. So if the path of the current has multiple paths to flow, we say that the elements or the circuit has having parallel components. Another definition to understand if the components are connected in parallel is that both the terminals of the elements will be connected to a common point. So you can see that diode D1 and D2, both terminals are connected to the same line. So we can say that they are parallel to each other. So this is basically the main definition of identifying the circuit with parallel components. So now here we have been asked to again determine the output voltage, the current I1, and these currents ID1 and ID2 flowing through the silicon based diode. So based on our previous understanding, we know that whenever the elements are connected in parallel, the thing that is common among them is the voltage, and we have seen this in our previous linear circuit analysis courses. So if we look at our circuit, we know that the 10 volt is enough to energize silicon or both the silicon based diodes. And in order for both the diodes to be energized, the minimum voltage they need is 0.7 volts. So as soon as both the diodes reach 0.7 volt, they are going to be in the forward bias direction, which means the voltage over here will be 0.7 volts. And since this diode 2 is parallel to diode 1, the same voltage is going to appear over here, and thus we say that the output voltage is going to be the 0.7 volts. So this is the output voltage which we have figured out based on our previous understanding of same voltages existing in parallel circuit. Now let us find the current. So the current is moving I1 in this direction, so I can apply the KVL in this loop. So if I apply KVL, I'm going to have the value of 10 volts minus 0.33 I1 minus 0.7 volt of the first diode D1 equals to 0. So I1 comes out to be 28.18 amps. Now let us use our intuition. We know that KCL says at any point the number or the amount of current entering equals to the amount of current leaving. This means that current I1 is entering over here and it is going downward, and the same current is entering over here and it is going downward. So what we can say is that this current I1 is basically getting distributed on two different branches. So we can say that I1 is basically 2I D1. So it is going to be what? 28.18 divided by 2, which is going to be approximately 14 milliamps. So the same current is going to be distributed in this path and on the other part. So the ID1 is equal to, we can say this is ID1 and it is equal to ID2. So this is our analysis using the KCL. You can even apply KCL individually and find, but you'll get the same answer, because we have that I1 is the amount of current entering. It should be equal to ID1 plus the second current ID2. So the KCL basically gives us this benefit to analyze the flow of currents, and the currents ID1 and ID2 is going to be half of the original current, which is going to be I1. Finally, let us look at a series and parallel combination combined together to find the unknowns, which is again output voltage V0 and the current I. So in this circuit, we have two voltage sources. One is at the 16 volts and the lower one is at the 12 volts. We know that the higher voltage is going to take precedence over it. So if you want to find the output voltage, we can just take a simple track, and the simple track is we use the KVL on this loop to get the output voltage. So the output voltage is going to be 16 volts minus 0.7 volts minus 0.7 volts, and this comes out to be nothing but 14.6 volts. That's it. So we have simply used one side of the equation to find the output voltage. Now if we want to find the current, we can just use this loop over here. So the current is going to be, we already know it's a difference of V0 minus 12 volts divided by 4.7 kilo ohms, and this comes out to be 0.55 amps. So that's the amount of current produced in this series parallel configuration. So this concludes our lecture, where we talked about the load line analysis for the given semiconductor diode and what happens or how we can find the unknown voltages and currents if the diodes are placed in series configuration, parallel configuration, or series parallel configuration combined. See you in the next lecture.